Hello, everybody. We are going through the course theory and applications in thermal and cold plasma. So, in that, actually, in our this introduction, we told that what will be starting in our first few lectures. So, we'll try to understand what is plasma, then what are its features, then how we can arrive there. And this plasma is basically a collection of charged particles, how to get those collection, and how does it behave, and why we will call a fourth state of matter. Then that whenever plasma comes, usually most of you know that some terms like Debye length and plasma oscillation, frequency, all these things arise. So we'll get to know all these things. And of course, as the course proceeds, we'll come to know many more features that are inbuilt within plasma, like this diffusion, mobility, collisions, and some elementary kinetics and MHD applications also will be coming to know in these lectures. So first, we start with introduction to plasma. And this is again, I am telling you that we are going to cover only thermal and cold plasma, and basically we will not be dealing with fusion plasma. And these are, in other way, it is called actually industrial plasma, because most of the things that we are familiar with in our everyday life and in the industries which are being used, they are mostly fall in this category, thermal and cold plasmas. So I would like to start with some examples which you encounter almost in your everyday activity and you are more or less familiar with, so that you can draw some interest to the subject and you may be eager to know what is happening inside. So first thing, what is plasma? The term plasma is a Greek word which means that something is molded or fabricated. The plasma in which we are interested is neither what we have learned in our biology courses or nor it is an object which is actually meant by the Greek word, that is something molded or fabricated. We can briefly define it as like that. Plasma is a large collection of positively and negatively charged particles sufficient to shield itself within a distance of characteristic length of interest into the system, and that we will call a plasma. Plasma is macroscopically neutral but microscopically non-neutral. Now when I am talking about shielding, the shielding is basically electrically shielding what we refer to. So many of the time we tell that the plasma is the fourth state of matter. The plasma was first introduced by Langmuir and Tonks in 1923. Actually, more than 99% of the universe is in the plasma state. Actually, this Earth-like object, or whenever we move around, wherever we go, we usually see everything is solid, liquid, or gas. It is rare that we find something in plasma state. But you know that it is really very uncommon and unlikely object in the universe, that Earth-like body, because most of the universe is in the plasma state. Actually, I always tell that this our Earth is run by fusion energy. This is why, because if there was no sun, then we would not survive. Now, if there is sun, then sun is basically giving its energy to us through fusion reaction. That probably most of you know. So sun and other stars, galaxies, ionosphere, they all consist of plasma. Now, whether we are not seeing any plasma at all in our daily life, it is not. Like the lightning discharge or the fluorescent lamp, the neon tubes in the advertisement, or electrical spark when we make a switch on, they are all something like plasma. Now, when we say that solid, liquid, or gases, so there, you know that we can distinguish them. Solid, you can tell it by touching that it is solid, and liquid, of course, again you can touch and say that it is liquid. And if it is gas, of course, we know that we can find it out. So whatever volume it gives, you just say it just occupies that complete volume. It is like that. Now, they are distinctly different from each other. But if we call plasma, and sometimes we agree that it is a fourth state of matter, then how is it different? It is it really a fourth state of matter? So sometimes I tell you like that look at the periodic table, you see that there are elements, maybe it is more than 100 elements are there in the periodic table, as you can see on the upper right corner. Now if we say that all these elements are alive, then you may not agree. Because if I say that it is iron atom, it is alive, or it is carbon atom, it is alive, or hydrogen or nitrogen, similar things. So that is what I have shown on the bottom circle. Some atoms like carbon, oxygen, hydrogen, nitrogen, calcium, iron, they are just scattered in that in some way. And definitely we will say that they are not alive. But on the lower right corner, you see that it is basically all these atoms which makes a human. And nothing is there within a human body which is not there in the periodic table. But the surprising fact is that when they are in a particular combination which is in our body, then the particular assembly of atoms makes a man alive, and the person can think, can walk, can behave in a particular manner, and is altogether completely different. Similarly, we will constitute plasma from some of these elements in the periodic table. It will start behaving in a manner which is totally different from solid, liquid, or gas when it comes to the plasma state. So that is the magical thing. And how it becomes different and in what way they respond differently, that is basically the subject of this study. So some striking features that makes plasma different from other states I have mentioned in this slide. So you can count some of them and you can try to understand that they are little different from what a solid, liquid, or gas behaves in a particular manner. Now we see that the first one is plasma is composed of electrons, ions, and neutrals, and they are separated from each other. Of course, electrons are there within the ions and within the atoms, but free electrons are also there in a plasma. Now, plasma is composed of charged particles. Very interesting fact is that plasma is macroscopically neutral. So, we can say that overall the plasma is neutral. The plasma is macroscopically neutral, but it is not microscopically. That is, if you go to a smaller and smaller volume, a stage will come when you will see that you are now able to see the bare ions or bare electrons. And that time, they are actually not non-neutral. So there will be some minimum volume requirement beyond which you will be able to say that the plasma is neutral, but not within that volume. Now, although plasma is macroscopically neutral, it can very well respond to the electric and magnetic field. That is very interesting. Something neutral, it will not respond to electric or magnetic field, that is quite expected. But plasma, although it is macroscopically neutral, it can well respond to electric and magnetic field, and in a very fascinating manner. And the way it can respond, that we'll come to know in detail in our later lectures. Now, when a specific external electric field is applied, then you know that the positive charge particles will move in the direction of the electric field, and the negative charge particle will move in a direction which is just opposite to that of the positive charge particles. Now, in a plasma, it happens sometimes that when you apply an electric field, both positive and negative charge particles, they move in the same direction. So that is very funny, isn't that? So that way it behaves in a completely different way as we are used to. So that is how plasma is very interesting. Now, when charge neutrality is disturbed, like suppose I am applying an electric field, then electrons are very light, so they will respond very quickly and they will move in a certain direction. But the ions, they are very heavy and they are sluggish, so they will not be able to move that fast. So there may be a momentary disturbance in the charge neutrality created in that region. Then what will happen? Once the cause is disappeared, then the particles will try to restore the charge neutrality because the electric field that is created because of the separation, but they will overshoot from their equilibrium position like a pendulum. So depending on the kind of plasma that you have created, plasma restores its charge neutrality through oscillation at a very particular frequency. So that is again a very characteristic feature of any plasma to exhibit, say, certain plasma oscillation frequency. We'll come to know about this and we'll derive expression for that also. Now, plasma can seal itself within characteristic distance, precisely determined by temperature and the number density of the charged particles. So the macroscopic volume, the minimum volume within which the charge neutrality will be maintained, is basically determined by the plasma temperature and the prevailing number density. Now, you know that plasma can behave as a refracting medium. Again, what will be the refracting index of that medium? That is again decided by the number density. So what we can say precisely that plasma temperature and number density, they are very basic characteristic features of any plasma which decides what kind of plasma we have created. Now I always like to start with real life examples, so that you come to know why we are studying this and why we should study this. Is there anything interesting that can be applied to some processes, or that can be useful to make something very interesting? So that is where I thought, and I made this collection of these videos for that purpose. So now I will explain one by one. The upper left corner, if you see carefully, you see that there are two graphite rods and there is a gap in between, a small gap. So here what is being done, they have been connected to a very high voltage and they are momentarily getting touched and then they are getting dragged out. And when they are dragged out after touching, you can see that the separation that we are maintaining is not big, it is small only. And the moment we are touching and taking it out, a huge arc, or you can say a flash, is getting created. And a plume that is coming out from that region. So what we are seeing that when you do this, that we are touching two graphite rods and taking them out, then a huge plume appears in the atmospheric air and that doesn't sustain for long and that disappears. So other than that, we are seeing nothing. Actually, what is the bright plume that you are seeing that is coming out? That is essentially a plasma that is being formed. It is basically some exaggerated version of what you see when you make a switch on and just off. That time you may see some spark. So it is just a bigger version of that. Now, when it is giving the bright plume, what is happening inside that plume? What you see here on the upper right corner. It is so bright that we are not able to see anything what is there inside. And is there at all anything inside? Like, we know the burning flames. There, we know that there is nothing much maybe inside, only the, this fuel, whatever, maybe it may be your candle or it may be your kerosene lamp, which is getting evaporated and they are giving the light through combustion. But here, this is an electric arc. The heating that is being done by mainly a passing current, and that is causing ohmic heating and giving a temperature 10,000 or above. That is very easily obtainable using arcs. So the thing is that how the current is passing, through which region the current is passing, is it possible to see? Is there any way to do that thing? So this is a natural curiosity of everybody, how the arc heating the gas and reaching the temperature what we are thinking about. And is it that always will get a very, very high temperature like 10,000 degree Kelvin, or it may be that it is not that high, or there is some way to develop a device which can reach that high temperature. Now this arc things usually give a very high temperature plasma that is known to people for quite long time. But exactly the mechanism by which it is giving that high temperature, it is usually not known. This is mainly because it is very difficult to probe a very bright plume and to understand what is happening there. If you want to put any probe, that will be definitely melt, because the tungsten, which is having some temperature melting point of 3500 degree Kelvin, that also will get melt if you are putting that inside a plasma plume of 10,000 degree Kelvin. Then what are the ways out? So this is one result what you are seeing here. It is really something very wonderful and very difficult to get, but you are able to see, and that way we can consider you lucky that you are able to see that kind of dynamics that goes on inside a plasma plume. So what we did, we used a camera to record the dynamics inside the plasma plume, but that is not an ordinary camera. It was a fast framing camera, and in the current video, we grab the frames at a rate of 25,000 frames per second. So you can understand that if I ask you, you take your mobile and take 2 snaps in a second, you will say, okay, I can do that. In a second you can do that. But if I say 10, you will say, okay, it is difficult. But if I say 100, you will say that is impossible. But now we are going to take some 25,000 frames per second. Then you will say, what about the intensity? That intensity is not allowing you to see whatever there is inside. Then what way you will just circumvent that problem? So this fast camera is having a facility which can cut the intensity. It will cut down, and finally only the brightest zone it can keep, and it can show the dynamics of the very bright, the brightest zone in the region. So in that case, what you'll do, you just you set your framing camera, first framing camera, in a way that it records only the brightest zone. Then what you will see the movement of the brightest zone, and this is exactly what you are seeing in the upper right corner, the dynamics that is happening within the bright plume that you have seen on the upper left corner. So the dynamics that is happening within that plume, that is now seen here. So the bright zone, what you are seeing there, basically the current path, because current through the zone through which it is passing, it is hitting that zone to the maximum extent. So, and those atoms which are heated to the temperature, they are radiating the most, and you are recording that path. So the path that you are seeing here, the zigzag path which is varying very, very fast way with time, that is basically the path of the current. Now you are able to understand the path of the current that is varying from one electrode to other electrode with time. And the upper right corner video, what you are seeing, that is recorded for only 0.6 seconds. Like the seconds and moves like that in 1 second, like tick. So 1 second is done, and half of that is 0.5 seconds. Now you see that within that second, whatever the dynamics that you have seen, that is being presented here. So it is just around half of a second, the complete video goes on. So you can understand now how fast this arc is moving in an open arc. When such arcs occur in open atmosphere, then the arc is free to move in any direction, and you know that because of buoyancy, the hot gas move upward, so the arc tries to move upward when it is formed. And because of the movement of the arc in upward direction or along the direction of the movement of the gas, the name arc itself appears because of that. So if I ask you why an arc is called an arc, you can say that because of that reason, arc never stays in a straight manner, it always forms an arc, and that arc need not be a perfect arc, it can be twisted kind of geometry as you are seeing over here. Now I told you that it is having very high temperature, okay? But how much high? Can it melt an iron rod? Or can it, reach some temperature if you use a special configuration? Actually, this subject of thermal plasma originated from here. When you are able to control this arc, which is now moving in a very erratic fashion, if you are able to tame this erratic arc in a way that it stays in a shape and continues to heat in a very, very well-defined manner, then you can reach a temperature which is well above 10,000 degree Kelvin. But if you allow an arc to move like this may not reach that high temperature. So the technology of transforming this arc, which is hovering here and there randomly, to an arc which is well stabilized in the sense that it is stabilized in a zone where the gas is passing and it is heating the gas in a continuous fashion and in a very, very uniform, regular manner. So in that case, you will be able to reach that high temperature. But unfortunately, when you are allowing the arc to move like this, it may not be able to heat the gas sufficiently to reach a very high temperature. The lower two videos basically showing those things. Now, what I have done actually, I have put a rusted iron rod. So the melting point of iron, you may be knowing that it is around 1600 degrees centigrade, somewhere there. So if the plasma plume is having a temperature more than say 2000 degrees centigrade, then it is expected that it will melt it. Now what we have done actually, we have put that rusted rod in between the two graphite rods where the plasma plume is coming up. You just see the lower left corner video, the plasma plume is coming up, and I have put that rusted iron rod inside this. And why it is rusted? Because I got that time during the experiment. So anyway, that iron rod I have put inside, and the flame is running, and you will see that after the arc is over, it is never able to melt that iron rod. At most what it is doing, it is making red hot, but not able to melt. So it is not able to reach that temperature. Now you will say, then you are saying about 10,000 degree Kelvin. Where is the temperature here? So the thing is that the truth is that you cannot reach that high temperature when the arc is not stabilized. Now it is like that, the candles. Candles give a flame which is very high temperature. If you search the net, you will be seeing that it is a temperature around 1000 degrees centigrade in the bluish zone. Okay, and it is no surprise there. But we know that in our childhood we have played, we have passed our finger through the flame momentarily and nothing happened to our fingers. Many of you have tried that kind of games. Okay, now why it doesn't happen? Because it comes in momentary contact. So when your arc is moving randomly like this, it cannot be in touch with the rod for a long time. So it is now hitting here, next time it will be hitting somewhere else, and next time it will be hitting somewhere other place. So it is not able to continuously hit the rod in a persistent manner. The same way our finger is not burned, the rod is not heated up. So what is required? It is required to stabilize the arc in a fashion that it can consistently and continuously heat the gas that is passing through that zone. And that is the technology of thermal plasma devices. What we have done, we have now taming that random arc within this plasma device. So what you are seeing on the lower right corner here, this is called a plasma torch. Plasma torch is a device where you are able to control the arc in a way that it persistently and continuously heats the gas that is passing through this zone in a manner that it is able to reach a temperature more than 1000 degrees centigrade very easily. Now, as a proof, I have done this. I have recorded this video. This video is recorded in an ordinary camera, and what you are seeing, the same rusted rod what I put over here, I have taken that and inserted bit below this flame. So the arc, whatever was there, that was moving very randomly, now it is very, very much stabilized, one through thermal pinching, and that because of the cold boundary layer, it is pinched near the central axis of this plasma torch. And whatever gas is passing through there, they are getting continuously heated by the arc, which is not now randomly hovering over here and there. So it is now passing through a channel which is not more than 10 millimeter. You know how much is the 10 millimeter? Almost the thickness of your finger. So it is not going anywhere beyond that. And because of that consistent and persistent heating, it is able to emanate a jet which is having a temperature more than 10,000 degree Kelvin, and we have measured the temperature often in this plasma jet, and it comes anywhere between say 12,000 to 16,000 degree Kelvin. Now, when you have inserted the same rod over here, same iron rod which was not melt over here, we have now inserted here, and you see that the plasma is able to melt that rod like a milk, like a splashing milk. It is inline melt and pushed away by the plasma jet. You can see the droplets which are coming out. So they are so interesting to see that the plasma jet is able to melt that iron rod which was not melt in the previous case when it was inserted in the open plasma jet which was hovering here and there. Now it is melt like milk in this plasma jet. So my whole purpose of showing this video is that you understand the potential of the plasma and potential of the technology of plasma devices. The same plasma arc which was not able to melt the rod here is now melting the rod in a profuse manner. It is melting almost instantaneously and inline. If you want to melt something by some heating agent, it may melt, but it cannot melt instantaneously. So for instantaneous melting, the temperature of the plasma should be much higher than the melting point of the material. So the exact temperature of the plasma, if you want to know, we will be discussing in our main course that will be coming up. So there are optical emission spectroscopy by which we can exactly calculate the temperature. But here, just to have a gut feeling, you will be having a feeling that okay, the temperature of the plasma plume is really very high when you see that an iron rod is getting melted instantaneously by the plasma. And what you understand from this video, that there is a necessity of learning the technology of plasma devices which can tame the arc and produce a plasma which can be beneficial to many applications of our interest. Now I will show you this another video in this. Here what we have done and we have developed an air plasma device which is doing the same thing. It is stemming the plasma plume, plasma arc, and it is producing a plasma of so long length. You can see here the video. It is throwing the plasma from the top of a table almost to the bottom floor. So we have put a tray that is filled with water so that it cannot damage the floor. Now this kind of plasma device which can develop so long plasma plume is basically a manifestation of the electromagnetic body forces which occurs inside the plasma device. Now, when a plasma arc is operating, the arc current is really high. It is easily more than say 200 ampere or maybe say 500 ampere. They are very common figures in these arcs. Now, this high current produces a very strong magnetic field. And as I have told you that the whole arc is contained within a channel which may be having not more than 15 mm of diameter. So within the short channel, you are maneuvering your arc. And whenever an arc is passing through, it is generating magnetic field, and that magnetic field interacts with the current, the J cross B body force. That actually pushes a thrust which may cause the plasma plume to come out like a sword, as you are seeing here. So what you learn from this video, that it is possible to generate a very large volume plasma just by understanding the electromagnetic body forces within a plasma device. So if you are able to manipulate or you are able to manage the device structure or electrode design in such a way that the electromagnetic body force within the plasma, within your plasma torch is shaped in such a way that it produces a thrust which is sufficient enough to throw the plasma to a much longer distance. So what benefit you are getting? You are getting length so high and temperature also becomes high because of the constriction of the plasma jet. Now, when the length goes high, you know that a cylinder gives you a much larger volume, so you are getting a much better plasma volume over here. So your process zone increases, so process efficiency increases, and because of the temperature, higher temperature, you can use it for relevant applications. Now, there is another fact which you need to consider. If I want to take a pipe and throw some water through that pipe, you will say that you increase the pressure, then the jet length will be increasing. It is true. And here also, when you are getting such a long jet, then people thought that it may be the pressure which is causing the jet to increase. Actually, we configured the electromagnetic body forces within the device through simulation in such a way that we knew that it is occurring only because of the plasma thrust, that is the J cross B plasma thrust. But when people told us that it may be due to your that pressure effect, what we did, we opened this part, this segment we opened, and this was anode, the bottom one, and cathode was above. So that pressure, if it is at all, that will be released within the open zone. So this zone is open, and from there the plasma is bulging out, that you can see in this third figure. So there is now no question of pressure buildup, because if pressure is there, then it will be released to this zone. Now you see that what a long plasma jet still coming out from the end of your anode till the ground. So now nobody has any question about that it is the effect of pressure, because pressure is anyway released over here and still the plasma flow is coming out. So simulation is very much necessary to understand the device design and to make a device work as per the requirement of your process. So we are able to develop this kind of device only because of proper simulation of these plasma devices, and that's why we came to know how to manipulate the electromagnetic body forces within this plasma device, so that you can get a very, very long plasma jet as you are seeing over here. So with this, actually, I stop here, and what we'll do, we'll meet in the next class and we'll discuss more about the plasma applications. And I will say that I am showing you all these plasma examples only to make the things that clear, that many of you may not be familiar with the plasma things. You might have seen the sun, but apart from that, I don't think that any processing plasma many of you have seen, except those who are already working in the labs. They might have seen those kind of plasma. But for others, before you enter into the course, you come to know that these are the plasma devices and how they can impact, and what is the necessity of learning the plasma device physics, and that what is the importance of simulation. So in the remaining of the course, you will come across all these kind of devices, how they operate, what are the kind of mechanism that is operating inside the devices. So this much now, and we'll meet in the next class. Okay, thank you.